we're getting into the first law of thermodynamics. And the first law of thermodynamics says, don't talk about thermodynamics. Just joking. That was a Fight Club joke, if you've seen that movie or read the book. So the first law of thermodynamics says the energy of the universe is constant. So that's one way to view the first law. The mathematical definition of the first law is the following. Delta E, right, which we remember delta E is E final minus E initial, equals heat plus work. Okay? So we talked about how energy can be exchanged from one form to another, right? So in this conservation of energy, or in other words, the energy of the universe being constant, we can't create more energy, but we can exchange it from one form to another. Heat and work can definitely be exchanged. So we can provide an engine with heat and it will do work for us. Okay, this is how your car works, right? You're burning all of that fuel, you're releasing heat from a combustion reaction, and it's driving this piston to move up and down, which causes a drivetrain to rotate, which causes your tires to move, so on and so forth, okay? Other ways to view the first law, so this delta E can refer to system or surroundings. However, if we now put specifically system or surroundings, we could always view that in the case, because energy of the universe is constant, the energy of the system, change in energy of the system, will always be the negative change of energy of the surroundings, right? Equal and opposite. Or E system plus E surroundings equals 0. Okay? So in other words, if my system gives off heat, then perhaps the change in energy for the system is negative, but then the change in energy for the surroundings will be positive. Okay? So this is just saying kind of what we saw in this diagram, right? That the heat flow will be opposite depending on if you view the system or the surroundings. In chemistry, we're always interested in the system. All right? So now, what about work and heat? Okay. Well, so we just talked about when delta E is negative, heat is leaving the system. And when delta E is positive, heat is, or I should say energy rather, energy is entering the system. But what about heat and work specifically? Okay, well, so here's another diagram where we have surroundings in yellow and system is this little green circle. So when heat moves into the system, we say Q is positive. So positive heat, positive Q means heat is going in. However, work can be done on the system too. We can do work on the system. And that would be in the form of a force acting over a distance. So remember, work is force times distance. And the easiest example of this that we're going to see in the next slide is compression. So imagine taking a balloon and we're forcing that balloon to be smaller. We're working on the balloon. We're pushing it, okay? And so because that's work being done on the system, as is showed in this blue arrow, work would be positive, okay? So whether we have heat going in or work going in, and specifically going into the system, those quantities will be positive. Now, what about the opposite? What if we have heat leaving the system, such as the example of an exothermic reaction? Well, we would say Q is negative. Okay, so the opposite of heat going in. When heat is going out, it's negative. Or when work is being done by the system, it's also negative. And if we think about this, if work being done on the system might be compression, squeezing that balloon down, okay? If instead it's the opposite case, if it's expansion, if perhaps our balloon is now expanding, it's actually pushing away the atmosphere, right? It is pushing the surroundings out. And so we call that negative work. We say the system is doing work on the surroundings, okay? So keep track of all of these things, system, surroundings, etc. Okay, let's do